No, you're the one who's better.
Okay.
I am not sure. Class is starting.
All right. So thus far we've been doing algebra, homological algebra, linear algebra, that sort of thing. And this class is computational algebraic. Thus far good. Topology. I'm going to bring you to topology. So today we're going to talk about simplicial complexes. And the benefit about simplicial complexes is that they are a combinatorial representation of spaces. Combinatorials. This falls in the landscape of topology. This falls in combinatorial topology. And the idea is that you build up spaces as combinatorial objects and do things with them. For those of you who have taken topology, this will have a somewhat different flavor. Rather than talking about the open sets, they're around, but they're not going to be really quite in the fore. So this will be a little bit different. The focus here is still on collections of points, but not so much their neighbors, but their local connectivity. So in contrast, not as much on neighborhoods. Now, given the combinatorial topological structure, that gives rise to the neighborhoods. And I'll show you how that construction works. And I'll give you, first of all, the general definition of an abstract simplicial complex. And then I will give you several different ways to cook up abstract simplicial complexes from other spaces that tend to show up in practice. And I'll show you how the neighborhoods come about. And if you've seen topology before, then you'll be in good shape. If you haven't seen topology before, well, it won't matter too much. Okay, so here we go. It will not be obvious from the outset exactly how this links up to chain complexes. We'll bring that in the coming classes. The chain complexes turn out to be a good way to analyze these objects. And that we'll build now. Okay. So, first thing we're going to start with is we're going to start with an abstract simplicial complex. So I need to define that for you. So given a set V, could be any set at all, set V, and abstract simplicial complex, call it X on V, is a collection of subsets of V such that if, call it sigma, is an element of X, so it is a subset of V. So type-wise, this is a collection of subsets. This sigma is a subset of V. So if I've got this sigma sitting there and delta is a subset of sigma, then delta is also V. So that's the definition. So it's a collection of subsets of some given set V.
Does that mean delta is an X or delta is a subset of V?
Is an X. My bad. Good catch. X. Thank you. So I started out with an element of my collection of subsets, so it is a subset, and examine that. If I find another subset in there, that subset's also already in my list. So it's closed under the operation of taking a subset. Now, it's useful to have a bunch of names to talk about these things. So the singletons. So single V, which is which is a subset of V, are called vertices. Single vertex, plural vertices. Pairs are called edges. Edges. If you've ever studied graphs in computer science, graph is a kind of simplicial complex, abstract simplicial complex. One in which all of the subsets of V that are in X are either vertices or edges. And the study of this is called graph theory. And there's lots of very interesting things you can talk about in graph theory. This is a little bit more general, a little more souped up. You can talk about a few more things, because now I can have triples and quadruples or any other tuples that I might like to have. Now, what this definition does enforce, though, is that if I do have an edge like this, then I have to have all the subsets, because if I have some subset, say V1 alone, that singleton, well, it's a subset, so therefore it must be my collection. Additionally, the empty set is always in there too. It's kind of annoying to write. I often forget to write it, but you're welcome to remind me if I forget. Okay. So let me give you some examples of these. There are lots of abstract simplicial complexes, and in many applications, this is the right tool to use. Okay, so some examples. So the first, most basic, most stupid example is just a single point. Here's 2 points. And those 2 points have nothing to do with each other. And here's 2 points with an edge between them. And of course, the fact that I'm using these words to describe them indicates there's a visualization. Here's V, here's V1, V2, and here's V1, V2, with an edge between. And this edge is what is labeled V1, V2. But this, as you can imagine, gets much more sophisticated. Start drawing much more complicated things.
One quick question. Is there any particular reason why you're explicitly stating the empty set?
Because I'm listing the entire simplicial complex.
Okay, so you would have to state. All right.
That's right. Now, there is, given any collection of subsets of V, there is a unique minimal abstract simplicial complex that contains that one. Simplicial complex generated by And that's totally fine. In many instances, it's better to save on representation. In other instances, you really need the whole thing. Really, it's sort of application dependent. For the moment, I'm being completely explicit writing about it. At some point, I will get very lazy and probably just draw diagrams and pictures rather than writing out these whole big, long, expanded lists. Okay, so that seems straightforward enough. What happens when I go up a dimension? Well, something like this. Instead of V's and W's, I use numbers. My set of vertices are just numbers. They don't have to be. There we go, they are. So there is a simplicial complex. I'm drawing it as such. I can certainly include all of the edges and label all the edges, but just purely drawing them in is quite sufficient to tell you they're there. Now, this one is somehow different from this one, which is then about all the rest of it. You're absolutely right. This gets very irritating after a while. And to indicate that what we've got going on here is not just these edges, but also this first guy, we fill in that face in the middle. Fill in that triangle. So what do you think happens if I've got 4 of them? What's it look like?
Three-dimensional shape, that's what
Yeah, like a filled-in three-dimensionally shape, yeah? What does it look like? It looks like, what's the name of this sort of shape? Pyramid-y thing? Yeah, it's a pyramid with a triangular base.
Tetrahedron?
Tetrahedron. Yes, tetrahedron. So if I were to add one more dimension to this thing, it would be a tetrahedron. The thing to notice is that, as my sets get longer, I get lots and lots and lots more subsets that I got to write down. It kind of gets obnoxious. Speaking to the computational side of computational algebraic topology, that can be a real pain. Yeah.
What indicates to us that for number 5, the triangle is filled in?
1, 2, 3, all together. Notice the difference, the only difference between 4 and 5 is this guy right here. The 1, 2, 3. And that 1, 2, 3 together says fill it in. Just like the 1, 2 says fill in between 1 and 2.
Right, okay.
If I had a 4 out here, and a 1, 2, 3, 4, it would say fill in this whole region in here. Now, if I had the 1, 2, if I didn't have the 1, 2, 3, 4, but I had the 1, 2, 4 in there, then it would fill in this sort of sheet in between here and here, this sort of triangular piece that would kind of come out of the board, or possibly I'd squash it over into the plane. Run out of dimensions pretty easily in this way. But there's really, in principle, no difficulty handling any arbitrary number of these guys put together. Now, I did use the word dimension, and in some sense, if you look at it, this dimension is kind of telling you the number of free parameters. If I've got just a vertex, there are no free parameters. I'm on the vertex and I can't move. If I'm on one of these edges, these pairs, it's kind of saying I'm somewhere between 1 and 3. Somewhere between 1 and 3, I have one free parameter. One free parameter to move along this edge, or say, similarly this edge. This 1, 2, 3 says that I have 2 free parameters. I can move anywhere on this surface, say this direction or this direction. So the number of free parameters to confine you to the surface seems to be one less than the length of that particular element of my abstract simplicial complex. So we've got some names for all these things, which I'll give you. So, some definitions. So if X is an abstract simplicial complex, and sigma is an element of X, so it's a collection. Sigma 0, V1 up to Vn. Then sigma is called a and n simplex. Wait, no, it's an n plus. Let's see here. It is a, yep, this is an n simplex. N is the dimension sigma. Or sometimes instead of calling it an n simplex, we call it an n face. And each delta, which is a subset of sigma, is called a face of sigma. Notice all the faces of a given simplex are of dimension equal to or smaller than that simplex. So if I have a simplex that's got dimension 3, that means it has 4 vertices in it, then all of its faces have dimension 3 or lower. Of course, if you include all the faces which are not exactly that same simplex, then their dimensions 2 or lower. Okay. Now, wanted to give you a connection of simplicial complexes to topological spaces, tell you about neighborhoods on them, or open sets, and indeed they are immediately available to us. So given an abstract simplicial complex, there is a topology associated with it. The topology is on the elements of the complex itself. The elements in this complex are the points in the space, not the vertices. So we throw that definition up there. And then I'll give you an example so that it can be kind of clear graphically what you're looking at.
Hey, Professor,
Yeah,
on those examples you just showed us,
yeah.
the entire set that was given, is that X?
Yes, each one of those was a simplicial complex.
Yeah.
Yep.
Okay.
Yep. There's an example of 5 different simplicial complexes.
And the subsets of the elements of the simplicial complex are called
Either faces or simplices.
simplicities.
Simplices. S-I-M-P-L-X is the singular, S-I-M-P-L-I-C-E-S is the plural.
So simplex is like the,
One of them. That's one of them,
right,
and this is more than one of them.
right.
I have occasionally seen simplexes, but that is for the uncouth. Sometimes too, you'll see simplex called a cell as well. Although I'm going to shy away from this notion here, because what cells tend to refer to is they tend to refer to something that's a little more geometric. So we'll just refer to simplex and simplices, or face and faces. But if you read some of the literature, you'll sometimes run across cell. And usually that's referring to something a little different, based off the same argument. Okay. Other questions? All right. So let me tell you how to construct a topology. So, given a simplicial complex, X, and a simplex, sigma in X, the star over sigma, ST sigma, or sometimes people will write it as the star over sigma, which is the set of all delta in X such that sigma is a face of delta. So that sigma is a face of delta, which equivalently, if you want to think about it purely in terms of sets, sigma is the subset of delta. This is some set of faces. They're set of faces of higher dimension. Here's the theorem. It's proven in 1937 by Alexandrov. Is that the collection of stars is a base for a topology. And that topology is usually called Alexandrov topology. In this paper, Alexandrov proved a little bit more than that, but this is quite sufficient for what we need here. So if you take a look at all the stars, you can think of the stars as open sets. Okay. Now, thus far, there's a big pile of symbols on the board. I want to make this a little more intuitive. And I think the way to do that is pictorially, because then you can see exactly what the topology is doing and what the neighborhoods that this cooks up are doing. And then once you've got this topology in hand, as you may know, that then you can talk about closures and other such things as well. Okay. So, here we go. I'll give you an example. Good copying this? Sorry, no.
I'll get it later.
No, go ahead. The point is, this is very, very intuitive and very physical, and this is a great definition because it, on one hand, it's very simple. On the other hand, it does exactly what you do. So rather than specifying by some big long collection of vertices and sets of vertices, which is kind of obnoxious, I'm just going to draw a two-dimensional simplicial complex, or a simplicial complex whose largest dimension is 2.
Did we define, oh, yes, we did, sorry.
What's that?
Yes, we defined that, yes, we did.
Yeah. So here's a simplicial complex. And you could write down that simplicial complex as an abstract simplicial complex by listing all the various faces that are in it. So certainly 1, 2 is in there, the singleton 1 is there, the 2, 3, 4 is there, etc. So you could draw this diagram in think of it as completely characterizing the set of sets. If you're writing this in software, you have to write out all those various sets, or at least enough sets that the computer can figure out the rest. It's pretty easy. If you wanted to do all of the sets that are necessary to generate it, well, you need this one, you need the 2, 3, 4 one, and then you need all of these other edges. And then these 3 edges come for free. Okay, so let's examine certain stars. Let's look at various stars. Well, let's start first off at 1. The star over the simplex 1. This is the set of all, now, simplices. The points are the simplices. The set of all simplices that include the simpleton 1.
One of the empty set.
Well, 1 and the empty set are certainly in there, but 1, 2 is also in there. 1, 2 includes 1 as a subset. All of the cells that include the one we're interested in. All of the cells of which sigma is a face. Did I get the definition wrong when I wrote this down? I don't think so. Oh, you copied it wrong. Okay. All right. So this is the set consisting of 1, 1, 2, but not 2. But not 2, not 3, any of the others. So it really looks very much like an open interval around 1. Contains 1 and 1, 2. Now what if I instead took a look at the star over this simplex, 1, 2? Well, what is that? Well, all of the simplices that,
It's going to be 1 dimension high.
yeah, well, basically it's just the interior of this thing, just this edge. No vertices. Now, it's a little different if I grab, say, 4. 4 is going to be a bit long. What's that? Oh, you're right, the empty set's not in there. Good call. My bad, I'm being overeager here. Yeah, the empty set's not in there. Okay, so if I grab the star of 4, what do I have? Well, 4 is definitely in there. 2, 4 is in there. 3, 4 is in there. 4, 5 is in there. And 2, 3, 4 is in there. So in essence, what it's doing is it's kind of taking something that kind of looks a bit like this. Sort of looks very much like an open neighborhood around this particular vertex. Now, if I instead sat at here on 3, 4, 3, 4, what is that going to look like? Well, it certainly includes 3, 4. Includes 2, 3, 4, and nothing else. Just this, the interior of this edge and the interior of this two sides. So now you can kind of maybe see why this works out to be a base for topology. Really, the only thing you need to worry about is the intersections. And anytime you intersect these things, are there indeed open sets around each point? Yeah, sure, because like they include each of these points, and you've included everything else as well. And that's basically how the proof goes. Basically, you take a look at the intersection, say, between 3, 4, and 4. You say, well, 3, 4 is entirely contained inside 4. If you looked at the intersection between the star over 4 and the star over 3, what is that going to be? Let's take a look at it. Intersection of the star over 4 with the star over 3. Well, what are those higher dimensional simplices that are connect to 4 and to 3, or contain both 4 and 3? Well, certainly 3, 4 does. What about 2, 4? 2, 4 in the intersection of those two stars?
No.
What?
It doesn't include 3.
Yeah, 2, 4 doesn't include 3, so that's out. And-
2, 3, 4 is
What's that? 2, 3, 4 though does, you're right, so 2, 3, 4 is in there. And that's it. There's nothing more in there. And if you look at that, you say, oh, well this is pretty clearly sitting just on top of 3, 4. You can walk around and do this kind of thing, pretty general. This is why it works. This gives you a topology.
So if you had one single point that wasn't connected with any of those,
Ah.
would you include the empty set with that then?
Good question. So the star over 9, what does the definition say? It is the set of all simplices that contain this simplex. So 9 certainly is in there, but does the empty set contain this set?
No.
No. So that's not it. That's the end of the list. Yep. Okay, so this forms a topology, and this is a very handy topology. It's very good for playing with abstract simplicial complexes. Now, closure does something also pretty useful. What closure does is it fills in all the lower dimensional simplices. It literally closes it off.
What's the star of the null set?
Everything.
Everything.
Because everything contains the null set. Yep. And when you think about it from a topology standpoint, your topology has got to contain everything. That's not a reasonable thing or unreasonable thing for it to do. All right. So what about closures? Proposition is that in the Alexandrov topology on X, an abstract simplicial complex, the operation. Let's just say the closure of some set. A set A, subset X. Remember, this is now a list of simplices of various dimensions. This list, this closure is given by set of all subsets of A. So, for instance, here's a small simplicial complex. If I take a look at the closure of 1, 2, 1, 2, 3. It's a set. This is some set in fact, let me make it even, not even an open set. This is a some subset of my abstract simplicial complex. It includes this vertex, this edge, and this face. If I compute the closure of this, I'm going to fill in all of those various subsets. So I'm going to get 1, 2, 3. Supposed to be 3. 1, 2, 3. 1, 3. 1, 2, 3, and the answer. So fill in everything. The closure squashes everything down. It gives you all of the lower dimensional cells. Okay, that's proposition. How does one prove this kind of proposition? Well, basically by direct construction. You just look at it and you say, well, I've got my complex. I ask, is an element, some random element, which is not my set A, but is one of the subsets of this collection of sets? And you ask, well, let me take a look at every open set around that. Special, neat thing about Alexandrov topology on abstract simplicial complexes is that there is a unique smallest open set around every set. This is not the case, say, in the real numbers with the usual topology. I can keep shrinking my open set down to a point. Lots and lots of open sets, but the last little singleton point on its own is not an open set. So I can't do that here. I can shrink down only to a point, and then I got to stop. And I come to the minimal open set. So I can just grab that open set, take a look at it. Every open set that contains that point is going to contain the whole thing. Ask, does that intersect this? Of course it does. Box checked. It's a limit point. It's a closure. Verbally, that's how the proof goes. You write it down real quick. And then I want to give you some examples of general constructions for how you can cook up some abstract simplicial complexes. Really play an important role in applications. You will see them over and over. Okay, so proof. Suppose X is in some element, let's call it sigma. X is a subset of sigma, which is an element of A. So I take my A, it's built up of a bunch of simplices, grab one of those simplices, sigma, and take an element which is a subset of that. I want to claim, I want to show that X is in the closure. Well, X being a subset of sigma means it's an element of X. In particular because X is an abstract simplicial complex. X is itself not just an element of A, but also an element of big X. So every open set containing X will contain the star over X. This is very specific to Alexandrov topologies. It's not true in general. And it has to do with the fact that there's only finitely many open sets. I can shrink, 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 shrink. Every point's got to be in some open set. So there's a lower bound. I've got a finite decreasing sequence with a lower bound. In fact, star is what it is. Okay, great. So I take that now, and notice that this star over X contains sigma. By construction. So every open set around X at least is going to touch A at sigma. So X is in the closure. And history. And a proof. Very nice, very crisp. So closures do really nice things in abstract simplicial complexes. They basically just fill in the boundary. Okay, so now some examples. And I want to talk about primarily two main examples. These are general examples. They're general constructions that yield abstract simplicial complexes. The first one is really very, very concrete, and the second one is a little less concrete. And to get the first one, which is the concrete one, it creates a specific kind of simplicial complex called a flag complex. So I'm going to tell you what that is, and then tell you how to make it. And you can even kind of run somewhat of a cottage industry these days, where someone has a graph model of something, graph data set, if you will, and merely by using this kind of construction, building out the flag complex, you can sometimes get additional information that wasn't available. Okay, so definition, a flag complex is an abstract simplicial complex X in which, flag complex, in which there is, well, in fact, it's kind of nice to build this up inductively, but it's in which there is a simplex. In fact, I'll say there is an n simplex for every, let's see, n simplex for every, well, what do I want to list here? Well, I want an n simplex whenever it is the boundary of all of the n of a collection of n minus 1 simplices. So whenever, let me say it this way. In fact, there's an n simplex, let me name it. The 0 up to the n, whenever x also contains, so this is best done inductively, every subset well, every proper, otherwise it's a circular definition, contains every proper subset. So here's the thing to keep in mind. This is a flag complex. Every proper subset, oops. Of cardinality. I'm thinking computer science here, cardinality. 2 or more. Right. This is a flag complex. This is not flag complex. And with my corner case in there, this is a flag complex. So permit myself to throw in a bunch of edges, but the moment my edges form out the boundary of a triangle, bam, you got to fill it in. And up in dimension too. So if I have 3 more triangles that come together at another point, I better fill that in too. So it contains every proper subset of cardinality, 2 or more. Whenever, so I have to have a simplex. Whenever I have every simplex, or every sub-simplex of cardinality, 2 or more. In some sense, this is like the reverse of the abstract simplicial complex criterion. This is saying it's closed up as well as down. And my general comment is if you're given graph data, this kind of data, in which the simplices have dimension all less than 2, a standard stunt is to do clique analysis or clique analysis. This is a clique, a completely connected subgraph. In essence, you can think of flag complexes as whenever I see a k-dimensional click or a k click, I paste in a simplex of dimension k minus 1. This is a fully connected, everything is fully connected subgraph that I drop into triangle. If I were to have a 4 here, I include all of those, we're good to go. Okay. Now, incidentally, am I allowed, according to this definition, and this is certainly true, although due to the inductive nature it's not as obvious, what happens if I take my not a flat complex here, and I add a fourth one like this? Still not a flat complex. But now, what does the inductive definition do? If I wanted to make this into a flat complex, say I wanted to flagify it, what would I have to do? Well, every time I see a particular set of subsets of cardinality 2 or more, they've got to be telling me that there's a higher dimensional simplex. So what do I have here? I've got 2, 4. That's in there. I've got 3, 4. And I've got 2, 3. So every time I've got this full list, this is the list of all the length 2 subsets of 2, 3, 4. Well, I better paste in that face. Similarly, I have all of the subsets of length 2 or more of 1, 3, 4 also, don't I? So I'm going to paste that one in. And then the back face, and then this bottom face too. Oh, but now by induction, I now have all of the length 3 subsets of this length 4, or 3-dimensional simplex. So I better fill in the inside too. And then that turns that into a flat complex. So this inductor procedure fills up. And if you just start with the graph and start flagifying, if you will, up by dimension, you'll fill up and you'll end up with a flag complex when you're done. Word to the wise, not computationally efficient. This process of searching for all the various possible subsets is very slow. Okay, but now let me give you an example of flag complexes in action that we tend to see in data a lot. And the kind of data that one often gets, this is especially big these days in big data and machine learning, you get a list of points in Euclidean space. And typically it's not like 3 dimensions, it's like 53 dimensions or something. Fine, whatever. Doesn't really matter from a theoretical standpoint. But if you have a list of points and you have the distances between them, you can start building a flag complex. So there's a complex called the Vietoris-Rips complex. Yes, and this is going to be a definition. If I have a space of points, or a set of points in a space where I can measure distance, a metric space. So x d is a metric space, which is to say this d thing is a function, takes pairs of points to real numbers to tell you their distance. If I start out with a metric space, and I have a collection of points, P is a subset of points, form the Vietoris-Rips complex.
It sounds like a good thing to call into work, to get out of, So I can't come in today, I have Vietoris-Rips complex.
Yeah, there you go.
So they'll tell you, stay home.
don't, hopefully you're not contagious, I see. Of P with diameter epsilon It's a real number, positive real number, by the flag complex in which, and let's see, I need to name it. Usually people call it VR sub epsilon of P, in which the vertices are points in P and because of this flagification, if you will, I could just specify the edges. And so I'd say that P1 and P2 are an edge in this complex whenever, well, the distance between them is epsilon or less.
Unless they're particularly restricted.
Very fun. I actually heard a talk this past month where there is some discussion about this because there are multiple definitions that float around about whether or not one or the other should be chosen. Punchline is, if P is a finite set, it doesn't matter. If P is not a finite set, you can define both of them. They both are perfectly reasonable. You'll see both of them out in the wild in literature. The one with the less than or equals has slightly better convergence properties and stability properties. Now, this is a computational class, so everything's going to be finite, so it doesn't matter. But from a theoretical standpoint, if P is not a finite set, you really probably should choose the equals. That equals is due to some recent work by Henry Adams at Colorado State. He's got a paper out on the archive. Final exam is coming up at some point. The final exam is going to be a presentation. Maybe someone wants to grab his paper and read it. His talk was pretty cool. Okay, so this is Vietoris-Rips complex. So what does it look like? Well, it's really graphical because there's all these distances. So let me show you. On the other hand, it has some defects. And those defects are remedied by another complex, which we'll talk about. So rather than doing all sorts of equations and whatnot, which of course you certainly could do, I'm going to draw some pictures. Pictures are more fun. Okay. And let's see. And I think one more is what I want. Yeah, we'll stick with these for the moment. Okay, so here are 3 points, 1, 2, and 3. Similarly, points 1, 2, and 3. These points are in two-dimensional Euclidean space, i.e. the board. I'm going to pick an epsilon. I'm going to pick my epsilon a certain size, and then I'll start changing it. Here's my epsilon. Yep, my epsilon is there, width of my hand. This is epsilon. So now what I'm going to do is I'm going to draw you the Vietoris-Rips complexes. So in this first case here, the distance between 2 and 3, is that less than epsilon?
Yeah.
Yeah. So that edge goes in there. Is the distance here? Nope, definitely not. What about over here?
It's unclear.
Unclear, less than or equal to maybe? I don't know. Definitely no. Okay. So now let me take my epsilon and make it a little bigger. We make it instead of 1 hand span. Let's see if I did this right. Yeah, good. 2. So this is the Vietoris-Rips complex for just epsilon for both of these. Now let me bump it up to 2 epsilon. Well, 1 and not quite, but definitely still here. What about over here? Yeah, definitely, right? No problem. What about here? Yeah, definitely. And here, yeah, definitely. But wait, I said flag complex. So I gotta fill this in. And over here, did not quite, well, let's see here, not quite. So you can see there's a little bit of a difference here. Maybe though, let's see, let me try to measure this one here. Ah, yeah, totally. This distance made it, this distance was just a little bit too long. All right. So you can see that they're a little different. Now, if I yet increase the distance to now a third hand span, well, that one, does this one change at all at this point? No way. But this one here now, finally, I made this distance and I fill this in. So the thing to notice here is these, as you change the radius, or the diameter rather, the Vietoris-Rips complexes you cook up are a little different. And so, the question then is how to pick that epsilon. Now, if you're an engineer, such as the sort that I definitely was before I became a mathematician, plus and minus on that, unclear, you would say, well, what is the best choice of epsilon? And we'll go with that. If you're a mathematician, however, you say, that's stupid. There is obviously no best choice of epsilon in all circumstances. So instead, let's consider the set of all such epsilons and work with that. This may seem to be completely unreasonable. However, you know, I was able to basically draw what happened at each stage. And there were only finitely many changes that happened. So the observation here is treating the set of all epsilons, although it looks kind of daunting, if I started out with a finite set of points, it's not really that bad. There are only finitely many abstract simplicial complexes I need to keep track of. And in particular, going from epsilon to 2 epsilon, I get to keep the epsilon Vietoris-Rips complex and just add a little bit more. Going from the 2 epsilon to the 3 epsilon, again, I get to keep the 2 epsilon Vietoris-Rips complex and just add a little more. So it's an incremental process. I only need to sweep through once. This is not too bad computation. In fact, this idea of varying through all of the thresholds leads to a concept called persistence. The concept of persistence asks the question, which of these features last for a long time or for a large number of my parameter choices, or for a long range or a large range of parameters. So which features remain for many epsilon? This concept's been around for a long time. It's been used in computer graphics for a long time. People have used this for studying abstract simplicial complexes. In fact, if you buy a fancy graphics card on your computer, what it is a special purpose machine for doing abstract simplicial complexes and doing linear algebra with them. Linear algebra because how you do shading for these sorts of things tends to involve a lot of linear algebra and transformations and whatnot. Additionally, it is an interesting point now, recently, there are stronger, more interesting topological features to which persistence can be applied. And we'll talk about a bit more of that when we get a little farther into the course. We need homology, though, in order to make something called persistent homology, which is a very handy tool. Now, this Vietoris-Rips complex is all well and good, but it does really have the decided disadvantage that you're building all flag complexes. You will never see here, in this situation here, something that amounts to this same complex, but without that 2-dimensional simplex. You'll never see this because the Vietoris-Rips complex says, is the flag complex built on? The flag complex never looks like this. This is not a flag complex. So it would be nice to have a kind of complex that's a little more flexible, doesn't necessarily have the requirement that it be a flag complex. And that leads to something called a Cech complex. And the way the Cech complex works is rather than starting with a bunch of points, we start with a bunch of open sets. So if we start with sets rather then points. We obtain the Cech complex. So, there we go. Addition. And in fact, the Cech complex is a special case of something called the nerve, which I'll tell you what the nerve is. So if I have a collection, 1, 2, of open sets in some space, some topological space. You can think of them as open sets in the plane, totally fine. Open sets in Rn, totally fine. Abstract open sets in some abstract topological space, also fine. So I take a bunch of open sets and now build the nerve N on this collection, 1, etc., in which the vertices are just the open sets. Remember, that could be anything. I build my abstract simplicial complex just on a set. I'm going to build it on a set of sets. Doesn't bother me. Are open sets. And UI1, UI2 up to UIN is in my nerve. It is a simplex. Whenever, well, I can't say that one is like distance from another because I don't have distance, but I can definitely tell if they intersect. So whenever I can take this intersection, in fact, let me start with 0 rather than the 1. Sorry about that. UI1 up to UIN. Whenever that intersection, that n plus one way intersection, is non-empty. So whenever those sets touch.
Why do we have UI0 and UI2?
Oh, because I didn't finish relating. Sorry. Okay, UI0, 1 up to n. So there are n plus 1 sets in here. That's an n-dimensional simplex. So I have an n-dimensional simplex whenever I have this mutual n plus 1 way intersection. So this is like all Boolean algebra stuff, Venn diagrams. Basically, this is the way you should think of Venn diagrams in some sense. Every time I get an intersection in a Venn diagram, especially a Venn diagram with like more than 3 or 4 intersections, starts to become a mess. This is somewhat less of a mess. I mean, still visualizing a 15-dimensional nerve on a 2-dimensional screen is somewhat daunting. Been there. But it's way better than a n-way Venn diagram, which is even worse. Okay, so let me show you a picture of this. And I want to relate this diagram to the Vietoris-Rips complex. I said the word Cech complex. Basically, the Cech complex is where I grab my open sets from the distance, the various walls in a topological, in a metric space. Okay, here we go. So, here's U1, U2, and U0. Its nerve looks like so. Here's U1, here's U2, here's U0. The intersection between U1 and U2, there is something in it. It is a non-empty intersection. That non-empty intersection corresponds to the presence of this edge. This non-empty intersection between U0 and U2 corresponds to that edge. And finally, this non-empty intersection between U0 and U1 corresponds to this edge. And we didn't ask for a flag complex, so this is totally the end of the story. Of course, if you've got this kind of Venn diagram going on here, if you compute its nerve, it is indeed filled in. Because now I have a three-way intersection, so I have two-dimensional siblings. In fact, there's a very, very powerful theorem, which I will state, I will not write because I do not want to be called out on the carpet to prove it, which says that if you've got a nerve of a topological space, so a nerve in a topological space in which the open sets form a cover, and furthermore, they form a very special cover in which all of the various intersections themselves can be squished to a point. If I can do that, then in fact, all of the topological information you might want to know about the space, up to homotopy type, is what it's called, is captured in the nerve. And that's a very powerful theorem, but that enables a lot of computation, because then you just work with these nerves. Now, from a computational standpoint, computing intersections of arbitrary sets, also not very much fun. Also computationally kind of awful. So it is often the case that what we tend to deal with, even though we want to be working with nerves, because they're way easier than working with the sets, we want to work with nerves, we can't. So instead we work with the flag complexes, or we work with Vietoris-Rips complexes. So there's some pluses and minuses there, but there is a nice theorem that says that the flag complexes and the flag complex of the nerve and the Vietoris-Rips complex fit together in a nice way. And it basically, by messing around with thresholds of the distances, you can kind of get one from the other, you can kind of intuit some of the features of the other. So in practice, even though the topological space is kind of the gold standard, we work with the nerve because it basically does what we want. In actual practice, we usually work with flag complexes, or at least often work with flag complexes, and quite often the Vietoris-Rips complex. In fact, if you look at most of the literature on computational topology, you'll see Vietoris-Rips complexes all over the place. And, well, if I have anything to say about it, you'll think about some of these others as well, because they're also quite nice computation. Questions on that? All right, see you next time.